Last lesson. Toughest lesson, most rewarding lesson. When we take the derivative with respect to time, we, instead of dy dxing, which is tangent slopes, we're going to find the change of something, a quantity, whether it's area, it's x, it's y, it's d, it's whatever. We'll find how that thing is changing at a specific moment in time. Okay, and we've dealt with it so far with velocity and acceleration, but now we're going to talk about objects, physical objects, distances, x distances, whatever, and we'll find out how those are changing. So we need to be comfortable with taking regular formulas that we've dealt with in the past, like an area of a rectangle, and we need to be comfortable with finding the instantaneous rate of change of that area. We need to be comfortable taking the derivative with respect to t of a, which is equal to LW. Now, it's not going to be hard as long as we kind of remember, you know, that kind of multiplication rule. The d goes with the a over the dt. And then with the L times W, we have to remember we use the product rule. So it'd be the derivative with respect to t of L, which is just dl dt, times W plus the derivative of W with respect to t, dw dt, times L. Okay? What this is saying is, if you want to find the change of the area of a rectangle, find the change of the length, multiply it by the width at that specific moment, and then find how the width is changing and multiply by the length, and you'll find how the area is changing in terms of like inches squared per second or feet squared per second. Okay, you can do the same thing with the perimeter of a rectangle. Perimeter is double my lengths plus double my widths. Well, if I want to find the rate at which the perimeter is changing, you would take the derivative with respect to t of it. This is dp dt. This is 2 dl dt. This is 2 dw dt. Okay? There's a bunch of others. Area of circles. We can find the derivative of this. Pi r squared. I won't do it. Circumference of a circle. 2 pi r. I can take the derivative of that with respect to t. dc dt is equal to 2 pi dr dt. If I want to find the distance between two things, we use the Pythagorean theorem. Okay, you want to find the distance from point A to point B. Well, that distance squared will be equal to your x squared distance, your horizontal distance squared, plus your vertical distance squared. And you can take the derivative with respect to t of that. And what's interesting is if you want to find how your distance is changing, well, you need to double the distance at the specific moment. And that will be equal to, times the change in the distance, will be equal to double your x distance times the change in your x distance, plus double your y distance times the change in your y distance. Okay, we can keep going on for other things, like a trig function of an angle. Tangent of an angle is equal to the opposite side, which is a y distance, over the adjacent side, which is a horizontal x distance. You can take the derivative of that with respect to t. Why don't we just do that, and then we'll move on. And I'll just do the left side. I don't want to do the quotient rule on the right side. We'd have secant squared theta d theta dt is equal to quotient rule. Okay? Volume of a cube, sphere, cylinder, cone. We can take all of those things and find how they are changing at a specific moment in time. Well, before we get into these problems, we need to be comfortable changing what is like a statement of something growing or shrinking or increasing or decreasing into calculus notation. So we need to express rates of change using this notation. So first example, the radius of a circle is growing at 3 inches per second. I could say the change in my radius at a specific moment or over the course of whatever time period they're talking about is equal to 3 inches per second. dr dt, the change in my radius with respect to time, is that. The perimeter of a rectangle is shrinking by 5 feet per minute. Well, the change in my perimeter with respect to time is equal to, now since I'm shrinking, my change is negative. Negative 5 feet per minute. Okay, area would be the change in the area, dA dt. And horizontal distance. If I thought about a horizontal distance between two things, what variable should I use? Should I use like d, or should I use h, or something else? X. We should use x with a horizontal distance if we think about a two-dimensional coordinate plane. So the horizontal distance is changing at a rate of -2 feet per second since it's decreasing. Okay? So we understand what ddting means. We understand how to take derivatives of formula. We understand how to change information into calculus notation. Let's start with the simplest related rates problem you will see. The simplest you already did for homework. This is just, I guess, the next step. The next step, and this is the only problem that's not in your packet. From now on, we're going to be doing problems in your packet after this problem. So easiest related rates problems were that problem 1 through 6 on your homework. This is step 2. This is maybe given the equation, but you have to produce the information that they gave you on your homework problem, and you have to figure out what you're trying to find. Okay? So maybe write this down really quickly. Really, all you have to include is this, and that. Well, what are we trying to find? That's always the first thing we should try to figure out. The rate x is changing, dx dt. Step 1, and we'll go over the steps, is to figure out what we're trying to find. dx dt equals something. Now, what other information am I given? That's another important thing. I'm given the rate that y is changing. We're told y is decreasing at a rate of 2 units per second. So I'm given dy dt is equal to -2 units per second. I'm given that I'm trying to find dx dt when x is 3/2. This is kind of information given. Now we have one of those homework problems. We're ready to figure out what dx dt is. And the only way I can get dx dt is if I develop an equation with dx dt in it. Well, take the derivative with respect to t of the equation you are given, and you will now develop something with the dx dt. Here's dx dt that I'm trying to find. Plug in 3/2 for x, plug in -2 for dy dt, and you succeed. -1/3. Okay. All right, that was the simplest. They're going to just get harder. Here are the guidelines. Huge guidelines. But maybe write a couple of these down. And everything else should make sense with just solving a word problem, you know? You're drawing a diagram. You're trying to figure out what you're trying to find. You're writing down your information that you're given. The key to writing down the information you're given is use calculus notation. You're going to make sure you know what the formula is that you're trying to figure out. Now, the thing that I'm going to tell you to really make sure of is to make sure you understand your fixed and your changing quantities. If your formula have more than 2 variables, we're going to want to make it an easier formula to take the derivative with respect to t. We're going to do that by substituting our fixed values or our variables in terms of another. But we're not going to substitute variable quantities at the beginning. Okay, you'll then differentiate your formula with respect to t, kind of just like we did the last problem. You'll plug in your info, you'll solve. Now we're going to get to as many examples as we're going to be able to get to. The remaining examples in your packet I will do, which will be in the video, which you can watch to refer. I think I also might create a video to help you on your homework, because you have to understand what's going on with the pictures that they're giving you for your homework. So look for that online as well. Now we're going to be looking at that first problem on your packet. So you don't have to copy these down anymore. All right, so once you start looking at that problem, so the growing rectangle has a fixed length of 10 inches and a changing width. At what rate is the area changing if the width is changing at 2 inches per second? Now, there are 2 ways to do this. I'm going to show you both ways. And I'm going to show you why I really put in bold and why I highlighted this, because it's going to make this problem easier one way than the other way, which should be a little bit more complicated. So we have a rectangle that's growing. I know. It's got a fixed length of 10 inches. So the length is 10 inches and the width is changing. It tells you right here that this length is fixed. That's very important to understand. This is a fixed L. It's not going to change ever. However, your width is increasing. Question is, at what rate is the area changing if the width is changing at 2 inches per second? Well, this is important. Using this statement, you need to develop this calculation notation to figure out what you're trying to find and what you have. So, at what rate is the area changing? What are we trying to find? Good, trying to find dA dt. Now, They say if the width is changing at 2 inches per second. That would be dW dt. Well, if I need dA dt, I need a formula with an A that deals with a rectangle. Area of a rectangle equals length times width. That's going to be my formula that's tying all these stuff together. That's going to help me find dA dt. Now, there are two ways to do this problem. And you'll see in your book or maybe online, one book will do it one way, some will do it the other way. I like to do it the easy way. I like to keep things simple. Here's how we keep things simple. Since the length is 10 and it'll always be 10, I can plug in the 10 for my length. It'll always be 10. It's never changing. Boom, I can plug it in. Now, I have all my information down. I know what I'm trying to find. I can go ahead and take the derivative with respect to t of this. The change in my area is equal to 10 times the change of my width. The change in my width is 2 inches per second. The A dt is equal to 10 times 2, or 20 squared inches per second. Why is it? Because this is 10 inches and this is 2 inches per second, giving me inches times inches, which is inches squared. Okay, that was the easy way. That's how I want you to do this. Now, the hard way that books do is they just differentiate this before plugging anything in. And they say, okay, I got dA dt is equal to dL dt W plus dW dt L. And then they said, okay, I'm trying to find dA dt. I know that my length is 10. I know that my width is 2, or the change in my width is 2. But I don't know what my width is at this specific moment, so I'm kind of stuck with just a W. However, the change in my length with respect to time is what? 0, because it's fixed. So they plug in the 0 there, and that's the other way you can find that dA dt is 20. It's an extra step. It's a more involved derivative. I like my way better. Plug in fixed values, you win. And especially when we deal with other formula like volumes of cylinders and stuff, you'll see that my way will reduce lots of headaches. Okay? Next problem. Spherical hot air balloon is being inflated. If air is blown into the balloon at the rate of 2 cubic feet per second, how fast is the radius of the balloon changing when the radius is 3 feet? They will most likely give you the formula that you need to use, so you don't have to memorize the formula for a volume of a sphere, 4/3 pi r cubed. It's good to draw a picture. All right. Mr. Davidson, what am I trying to find? Good. It's coffee. What other information am I given? What is? It says air is blown into the balloon at a rate of 2 cubic feet per second. So yes, we know 2, but what is that equal to? Good. Now, not just volume, but the change in your volume. So I'm trying to find dr dt when the change of my volume is 2 cubic feet per second. And I also know that I'm trying to find this when r is equal to 3. Now let's think about this r that's equal to 3 and this radius right here. Is this radius a fixed value? No. It's a value that is going to be changing because the balloon is getting blown up. The radius will be always expanding. So since it's a variable quantity, it is a changing quantity, I am not going to plug this 3 in to that r. Not going to do it. Instead, you will derive the equation first, and then you'll plug it in to find the specific change of this radius at this specific moment. Variable, don't plug in until after you differentiate. So I get v is equal to 4/3 pi r cubed. I got all my information down. I don't have any fixed quantities that I can plug in. So I take the derivative with respect to t of it. I get dv dt is equal to, now 4/3 pi, it's just a constant, so just leave it off to the side. Take the derivative of r cubed, 3r squared, dr dt. Now I have all the information I need to find dr dt. I have dv dt is 2. I have r is 3. Then I solve just by dividing all that stuff. Why don't we just simplify that stuff really quick? This is 9 times 3, which is 27. 27 divided by 3 is 9. 9 times 4 is 36. So this is 36 pi. Divide both sides by 36 pi. dr dt equals 2 over 36 pi, which is the same as 1 over 18 pi. You will be given calculators to do these problems, just so you feel comfortable with your solving. But for this, you'll be okay. All right, good. So that's another simple one. Third simple one. A cylindrical tank is losing water at a rate of 10 cubic feet per minute. If the radius is 10 feet, how fast is the height of the water changing? And the radius is the radius of the cylindrical tank. I will tell you that the volume of a cylinder is equal to pi r squared h. I want you to try this guy. And I'll do it as well. And we can talk about what your thought process was versus mine. That's not water. How do we do? Good. Anybody need me to walk through any particular steps?
Can you just do the label, how you know it would be -1/10 pi length of length?
Oh, the units you're saying?
Yes.
So you're talking about a height changing. Is a height like in units squared? Units squared is area. Units cubed is volume. Units are just lengths. So if this is -1/10 pi and it's dH dt, is it squared, cubed, or just units? Yeah, just feet per minute. Was that your question? Okay. Good. All right. So those are easy ones. These are also easy, but it's a little different. Told the growing rectangle has a length that is twice its width. How fast is the perimeter growing if the width is growing at 5 centimeters per second? So back to my rectangle. However, I'm concerned with the perimeter. And I want to know dp dt. And I'm told that dw dt is equal to 5. Well, I got A equals LW. Oh, that's the area. I got P is equal to 2L plus 2W. However, I'm not given a length or a width at all. I'm just given the rate at which my width is growing. And I'm told that the length is twice the width. If I take the derivative of this, I'm not going to be able to do anything. I don't know what dl dt is. So let's go back. We're stuck. Let's use the information we gave that was given to us to maybe simplify this perimeter equation. The length is twice its width. So if this is the width and this is twice the width, this is 2W. So the perimeter is twice my length, so that's twice the 2W. Plus 2W. All of a sudden, my perimeter is just 6W. Now, after using this relationship, I can take the derivative with respect to t to figure out how my perimeter is changing. The 6 times the change in my width. So that is 30, and perimeter is just in centimeters per second. Okay? Now, the next problem I'll do later. I'll tell you, you do not have enough information, so just say at h equals 2, or when h equals 2 at the end. And I'll do that problem later. Let's go to a medium difficulty problem. We're going to do this latter problem next. We're going to start with the space shuttle problem. Okay, and then we'll come back and you guys are going to do the latter problem. So we got a person watching the space shuttle launch. Okay. And the person is 3,000 feet from the launch pad. The question is, how fast is the distance between the person and the shuttle changing when the shuttle is 4,000 feet high and rising at a rate of 800 feet per second. So what am I trying to find? The change in my distance. How much it's changing. Well, I'm going to use d. I'm wondering what d dt is. At this specific moment, when the shuttle is 4,000 feet high and it's rising at a rate of 800 feet per second. Well, this 3,000 feet and this distance, what formula do we use with distance? Maybe that'll help us determine stuff. Pythagorean theorem. So we got d squared is equal to x squared plus y squared. Good. So this 3,000, what can I label that as? X. Is this a fixed or a variable length? Very important to know that. It will help us out tremendously. Now, this rise of 800 feet per second and this 4,000. This 4,000 feet would be considered a what value? It's a variable, and what variable would we use for it? A y. This is a vertical distance. It's a y, but this is changing. This is variable. So we will not plug that in until after we differentiate. However, this 800 feet per second, what can I say that was equal to in notation? dy dt. Good, and it's positive. So we have all of our information. We have our fixed quantity. Let's plug in our fixed quantity because that's never going to change. It's not going to hurt anything if we do this. We are ready to find the derivative with respect to t of this guy. So let's do it. Now, we have to make sure we take the derivative correctly. Mr. Brewer, what's the derivative of d squared?
2d dd over dt.
Good. 2d dd dt. Ms. Moore, what about the derivative of 3,000 squared? Good. It's just 0, goes away. We don't have to worry about that. We just need the 2y dy dt. All right, we're trying to find d dt. That's right here. I know that y at this specific moment that I'm trying to find this d dt, that y is 4,000. I know the dy dt, that's 800. You can plug in that. But I also have this d still there. I need to find d. Similar to how on your quiz you needed to find the y value with the x. If I have this d here, I need to find d. How do I find it? Use your original equation. So d squared is equal to 3,000 squared plus 4,000 squared. You can use your calculator, or you know, a 3, 4, 5 triangle. So you then plug in 5,000. I have space. Good. So that's 10,000 dd dt is equal to 832,000 times 2, 64,000. Divided by 10,000, that's 640. Or just 64. Did I get this right? 640? This was 5,000 times 2, that's 10,000. Did I miss a 0 here? Yeah, 5 zeros. I was way off. Then 1, 2, 3, 4. Get 1 0 left over. Good, 640. Okay, and this is in just distance units, so feet per second. All right. Ladder problem. You're up. We got a wall. We got a ladder against the wall. The lower end of the ladder is being pulled away from the wall at a rate of 2 feet per second. The question is, how fast is the top of the ladder coming down when the ladder is 6 feet above the ground? And we're told the ladder is 10 feet. Figure out what you're trying to find. Figure out the information they gave you. Figure out which values are fixed, which values are changing. Plug in your fixed values. Differentiate. Plug in your changing values. Figure it out. -32. -32 over 12, which is -8 over 3 inches or feet or whatever it is. Feet per second. Sorry about the mess. Let's move this over. Questions? How did we do? Thumbs up, thumbs down. In between? Where did we make the mistake? if we made a mistake? Who is brave enough to offer up the mistake that they made? Ms. Hicks?
I think if it was negative or not.
Okay. So, you know, if you're pulling the ladder to the right, in this direction, this x is positive. So if you just keep track of everything, you should definitely see that that has to be a negative, because if I pull it to the right, this has to move down. I don't want you to assign a value. If you did everything correctly, the value will make sense. You don't want to say, oh, this has to be positive, so you change it. No, it should make sense. We're moving down if the ladder's pulled out. Ms. Quinn?
So even though in this problem the y value is like a variable, like it's changing, you can still plug that number in when you're trying to find x.
You plug it in at the end, because the question is asking us to find how much the top of the ladder is going down at this specific moment. So it will always be at a height of 6 feet above the ground. It's at this specific moment, when the height is 6, how fast is this moving down?
So, but when you plug it into the original page and define right there, define x, you can plug that number in even though you're changing it.
Yes, because this is a scenario of, hey, at the moment in time when it's 6 feet above the ground, how far is away at that time as well on the x. So that's when it's okay to plug it into your original, because you're finding the situation at that specific moment in time. Okay, so good. Let's do a medium hard one. The hard ones will be on the video. This makes it medium hard because we're using trigonometry. So it's the same as the shuttle problem, same situation. So get your dude back, 3,000 feet away, drop him down there. Oh, that's perfect. And it's going up at a rate of 800 feet per second. We know that's a dy dt. The question is, how fast is the angle of elevation changing between the two when the shuttle is 3,000 feet high? What am I looking for? d theta dt. So let's think about this situation. Angle of elevation means this angle from the ground up to the top of the shuttle. We use the variable theta to denote an angle. I'm trying to find d theta dt. Well, I'm not going to use d squared equals x squared plus y squared, because when I take the derivative of that, I don't have a theta. I don't have a d theta dt. So what should I use? Let's use tangent. Let's use sine. Let's use cosine. In this situation, I have an opposite side that I'm given, a y, at a specific moment, and I have an x that I'm given that's fixed at a moment. Let's use tangent. Tangent of theta is equal to y over x, opposite over adjacent. But what can I do in that formula? Y over 3,000. Make it an easier thing to work with before we take the derivative. Okay, we're not going to plug in this 3,000. This is changing. But this x of 3,000 I will. Now I'm ready to take the derivative with respect to t. The derivative of tangent theta with respect to t, let's think of the chain rule, is the derivative of the outside, leave the inside, times the derivative of that theta. There's that d theta dt that I need to be able to find what it is. Now over here, I'm just going to go ahead and make this 1 over 3,000 dy dt. That's simple. Well, I know what dy dt is. It's 800. So that's 8 over 30. What am I missing? The theta. I can't figure out what d theta dt is until I know what theta is. Now, in this situation, it's easy. I have an isosceles triangle, 3,000 and 3,000. I know that has to be pi over 4. But it won't be easy, and you will have to use your calculator to find some of these angles. So get your calculator out and make sure we know how to find an angle using our calculator. It's a little bit of a review. Now, make sure your calculators are in radian mode, first of all. Second, we're finding theta. Well, you find theta using your original equation, okay? The tangent of theta is equal to y over 3,000, but since it's at the specific moment, so at y equals 3,000, you can say just the tangent of theta is equal to 1. Now, how do I solve for theta here? Inverse tangent of both sides. Exactly. So you go tan inverse or arctan of both sides. Tan inverse of tan is just theta equals tan inverse of 1. You should get 0.7853981634. Don't cut that off. Don't round that. Leave that. But go ahead and plug in pi over 4 and check to see that it's the same answer. Okay? So we get that decimal or pi over 4. Now, if you're going to use that decimal, you need to plug that decimal in the entire way. Okay? So you can either store it. Now we need to figure out what the secant of that value is. Of course, we can do this by hand, but if you have a calculator, remember it's going to be secant of the value squared or 1 over cosine of your value squared. So with that decimal, what you're going to do is you're going to go 1 over cosine, and you can plug in the answer. I don't know if you guys have ever done this. Probably you have. So we did tan inverse of 1. We got this decimal, which is pi over 4. I'm going to go in parentheses 1 over the cosine of that value, second answer. You guys done that before? Yeah. All right, good. Squared. It's just 2, okay? That's because cosine of pi over 4 is root 2 over 2. 1 over root 2 over 2 squared ends up just being 2. So I got 2 d theta dt is equal to 8 over 30. You get d theta dt is equal to 8 over 60 rads per second. Okay? So notice we did not get to the couple hardest problems. Well, those are your responsibility to know how to do. You got to watch the... All right, next problem. Hot air balloon problem. Rising from the ground, being watched by a spectator 400 feet away. Okay, so I'm going to assume we're 400 feet away on an X distance. So here's a dude watching a hot air balloon rising. This dude is 400 feet away. That I know is an x distance, and that's a fixed distance. It's important to know. Question is, how fast is the balloon rising? So that's a dy dt that I'm trying to find when the balloon is 400 feet off the ground. So that's a y value. That is a changing value. If the angle of elevation between the person and the balloon is increasing at 0.14 rads per minute. So we are dealing with angles here. This is theta, and we are told that the angle is increasing at 0.14. Of course, this is a changing value theta, but we will be able to find theta at a specific moment. All right, so I need dy dt. I have an x, I have a y, and I have an angle. Best trig function I can think of to use to do this would be to use tangent again. Tangent of an angle is equal to my opposite side over my adjacent side. Well, this 400 is fixed. This x distance is fixed. I can plug in that 400, thankfully, to simplify my original equation so I don't have a derivative and have to use the quotient rule. I'm going to go ahead and take the derivative now after I simplified it, and I'll see what I get. I get secant squared theta d theta dt is equal to, I'm going to put the 1 over 400 over here, times dy dt. Good. Well, I know dy dt. That's what I'm trying to find. So I don't know that, but I do know what d theta dt is. So I have secant squared theta. D theta dt is 0.14. I have 1 over 400 dy dt. Well, I need to find theta if I'm going to solve for dy dt. This is what I'm trying to find. So that means I need this. Well, I'll find theta using my original situation and knowing that we're trying to find how much we're rising at the specific moment when my height is 400 feet. So I'll say the tangent of theta is equal to my y, which is 400, over my x, which is 400. So 1. Well, you can know that we have a isosceles triangle. Theta must be equal to pi over 4. So we have the secant squared of pi over 4, similar to the last problem, times 0.14 is equal to 1 over 400 dy dt. Secant squared of pi over 4 we found from the last problem is just 2. So I have 2 times 0.14 is equal to 1 over 400. So in my calculator, I'll take 2 times 0.14 times 400 to find the change of my y distance. At that specific moment, we are going up 112 feet per minute. Perfect. All right, to the hard problems. We need to generate the correct proportion to do this problem. We got a lamp post with a height of 20 feet, shining a light on a 5-foot tall person 10 feet away from the lamp. So let's get a lamp post. Lamppost has a 20-foot high. That's like a y coordinate. I'm going to say that is definitely a fixed value. The lamppost is not going to be changing in the height. We got a 5-foot tall person who's 10 feet away. I'm not sure if this is fixed or changing. Let's see. This dude is 5 feet tall. That's definitely a fixed value. And he's creating a shadow. Here's a shadow of the dude. The question is, how fast is the shadow increasing? So let's give the shadow a length. Let's call it S. Okay? The question is, how fast is the shadow increasing? So what is the SDT, the change in the length of the shadow, if the person is walking away at a rate of 2 feet per second from the lamp? So this dude is moving at a rate of 2 feet per second away from the lamp. So the shadow is going to be increasing. That makes sense. As we get further along, we have a longer and longer shadow. But this 10-foot mark, this is a variable. Okay? So I can't use this 10. I'm going to have to say, okay, we have an X distance, and we're going to try to figure out what this DSDT is when this X distance is exactly 10 feet. Okay? Because I'm walking away. So the shadow is going to be changing. This is a variable. I'm moving away. This is a variable. This 20 feet is fixed. Well, you'd think I would use like the distance formula to figure out the shadow, but it's actually going to be easier than this. What I have is a set of similar triangles. So I have a triangle here on the outside that must be proportional to the triangle here on the inside. Well, that's going to be the proportion I'm going to use to help solve this situation and find DSDT. I know that the length from the pole to the end of the shadow divided by the length of the pole. Let's just go pole first. It doesn't matter. Let's do the length of the shadow and the distance. So the X plus S divided by the height of the shadow, or height of the pole. That needs to be equivalent to the length of our shadow divided by the height of my dude. Well, this is it. This is what I'm going to use to take the derivative of to find DSDT at this specific moment. But I can make it easier to work with by simplifying this. Multiply both sides by 5 and 20. I get 5x plus 5s is equal to 20s. I then can subtract 5s. I get 5x is equal to 15s. I can even divide both sides by 5 if I wanted to, but let's just go ahead and, yeah, let's go ahead and do that. So I get x is equal to 3s. Well, I'm ready to now take the derivative with respect to t of this, and let's see if we got something. We got dx dt is equal to 3 ds dt. So this whole 10-foot thing actually didn't even matter, because it turns out the way my shadow will be changing will just be the way that I'm moving divided by 3, and that'll be it. The length of my shadow will be increasing by the rate at which I'm moving divided by 3. That's it. And this is going to be in feet per second because it's just a distance. Okay, moving to the hardest type of problem. So I need to substitute correct variable in terms of another using proportions, and I'm going to also use the proportion to find the missing values. Let's do this. Is this the last one? Yeah, all right. We got water draining from a conical tank with a radius of 10 inches and a height of 25 inches at a rate of 3 cubic inches per second. What is the rate that the radius is changing when the height of the water is 15 inches? So I believe it wants to say what is the rate that the radius of the water is changing when the height of the water is 15 inches. That's very important to know. So let's draw our situation. I have a conical tank Here is a conical tank. We are told the conical tank has a height of 25 inches. So this is a fixed value. This is always going to be the height of the tank. It's not going to change. We are told the radius is 10 inches. That's not going to change. Let's talk about the volume of a conical tank. It would be 1/3 pi r squared h. That's good to know. All right. What else do we know? Oh, we know we have water in here. So I'm going to just draw some water. And this water is going to have a radius. And this water will have a height. And I'm wondering the rate at which the radius is changing when the height of the water is 15 inches. Like, how much is this shrinking? Okay, so this is an R, and I'm trying to find this change, this dr dt. Okay, well, there is a certain proportion that we will use, and this is an h, of course, and this h is changing. This is not a fixed, because the height will be going down as the water is leaking out here. So the height is variable as well. Let's see what happens when I just take this and take the derivative. Maybe I'm like, well, I got an h, I got an r. I'm going to do the volume of the water here instead of the volume of the cone. So I'm not going to be able to plug in 10 or 25 because those are fixed values, whereas my height and the radius of my water that is draining, that's changing. So if I took the derivative of this, let's see what happens. I am told also, I might as well write this down. Water is draining at a rate of 3 inches per second. So I'm trying to find dr dt of this water. And I know the volume of this water is decreasing at 3 cubic inches per second. So let's see what we got. We got dv dt is equal to, if I took the derivative of this, I'd have to use a product rule. And I got h's and r's, and it's going to look really messy. Let's see. I got 2/3 pi r dr dt, that's f prime h, plus the h dt times 1/3 pi r squared. Well, I mean, I could start plugging stuff in, but, I know what I'm trying to find. I'm trying to find dr dt, so that's here. But I don't know what the height is doing, right? No. I know the height is 15 inches, so I can plug in h and plug in 15. But I don't know how the height is changing. Well, that's a problem. So dh dt is a problem here. I don't know what this is. So let's go back. Let's kind of start over, and let's see what we should do. What I always want to do is try to simplify this before I take the derivative of it. It's very important to do that because you might get confused. You might not be sure what you have and what you can plug in and what you can't. So let's see if I can simplify this. Well, here are another set of triangles. Here's a triangle here, and here's a triangle here. We have proportional triangles. We'll use those triangles to our advantage. The triangles are the radius of my water over its height has to be proportional to the radius of my cone over the height of my cone, the tank. Well, I can kind of solve one of these for r or for h. Now, I want to find dr dt, so I kind of want to leave r in my formula. So what I'm going to do is solve for h so that I can plug in r's instead of h. So I get r times 25 divided by 10 is equal to h, or 2.5 r is equal to h. which I don't love, why don't we use a fraction? Let's go 5/2 r is equal to h. Okay, that's cool. Let's use this. So I'm going to go back and say, all right, the volume of my water is equal to 1/3 pi times my radius squared. And now my h has to be 5/2 of my radius. Well, now I can simplify this, and now I have an equation that can easily be derived, and we won't have to worry about any products. So I have 5/6 pi r cubed. I can take the derivative now so that I can find dr dt. I have dv over dt is equal to 3 times the 15 divided by 6. I can make that a 5/2. Pi r squared dr dt. I'm trying to find dr dt. I'm given dv dt, but I don't have r. Frustrating, right? But now we can actually find r. I'm given that I'm trying to find r, this radius, how it's changing at the specific moment when the height is 15. So to find r, I'm going to use this proportion. My radius over my height of 15 at that specific moment is equal to 10 over 25. So let's just simplify it. My radius over 15 is equal to 2 over 5 times 15. That'll be 3 times 2, which is 6. So that's my r. Now I can find dr dt finally. 5/2 pi times 6 dr dt. I get -3 equals 15 pi dr dt. Dr dt is equal to -1/5, 1 over 5 pi, something like that. Okay, that is in inches per second. All right, so definitely the hardest problem. We have the volume of the water formula, but we need to use a proportion to establish the relationship between the radius of my water, which is changing, and the height of my water is changing. I use that proportion to plug into my original equation to get a simpler equation. Once I have this simpler equation, I then take the derivative with respect to t. Once I do that, I notice that I have to go back and find r at the specific moment when my height is 15. So to do that, I use my proportion that I established again to find that r at that specific moment. Using that proportion, I figure out that r has to be 6. Once I do that, I can plug it back in here, simplify, and solve. And that's related rates. Hoorah. Make sure that's it. That's it.